Namaskar. Today in this lecture series of mechanics, we will discuss the application of calculus of variations for isoperimetric problems. Isoperimetric problem is a very famous problem which relates the area of a geometrical figure to its perimeter. Actually, in this problem, we determine the plane figure which encloses a greatest area such that its length is specific, or you can say its length is fixed. So the problem is that we have to find a figure. We have to find a closed figure such that the figure is enclosing area. Area should be maximum. Area should be greatest, and the length is specific. Length of that means the length of the enclosing curve is fixed. So naturally the solution of the problem was known to ancient Greeks. This was also posed by Greeks, and the answer was circle. But its rigorous proof took a long time to come to picture, and this problem was extended in multiple ways. The curves were extended to surfaces, and the area or the region was extended to higher dimensional spaces. If I talk about the physical explanation of this isoperimetric problem or physical manifestation of this problem, then I can take the example of the drop of water. You know that the drop of water, the shape of the drop of water is always spherical. At one stage, its shape is spherical, and the content of the water is fixed. So there is a force which gives it a shape of sphere, and that is the surface tension. So it is the force, surface tension is the force which makes its surface area minimum and maintains its shape. So the content is given, content of the water is given, and surface area is to make minimum. So this is one example of isoperimetric problem. The classical isoperimetric problem in a plane is given as, among all closed curves, you have to find, here the word is written closed curve. There I was saying a figure in the plane. So that also means the closed figure, or the figure bounded by the closed curve. So among all closed curves in a plane such that the perimeter should be fixed. So I have to find a curve which is enclosing the greatest area. You may have so many curves, like you may have this curve, you may have this curve, you may have this curve, and all these curves are having the same perimeter, and all these are closed. Now the question is, I have to find that shape, or that shape of the curve, that shape of the figure which is enclosing the maximum area, greatest area. In another way, you can say that among all closed curves in the planes of fixed area, now you fix the area, you have to find the curve of least perimeter. So if you write in first way, you have to say the greatest area. If you write in second way, you will write the least perimeter. So if you look at the statements, you see you have two things in this problem. One thing is you have to find the closed curve such that the perimeter is fixed, and the second is that the curve should enclose the greatest area. So you have a functional functional is area which should be greatest. You have one functional area which should be greatest. That means you have to extremize area functional. And there is certain condition. This is a condition that perimeter should be fixed. So this is the difference between the calculus of variation, which I explained to extremize or to find the stationary value of some functional. Here you have an additional thing, that you have some constraint also. So it is a problem subjected to a constraint. This is the difference. And this classical problem, isoperimetric problem, is conceptually the problem of least action in physics. The problem of least action in physics says that what action encloses the greatest area with least effort. What is the problem? Problem of least action. What action encloses the greatest area with least action. In 15th century, German philosopher Nicholas of Cusa gave an answer of this question. He said that this action should be rotational action. This should be rotational. So he said that the rotational action will provide the greatest area with least action. Now you can very well imagine that what this rotational action will provide. This rotational action will provide you a circle, and this is the process by which the universe was generated. So this is also the concept of isoperimetric problem, which was used by Kepler while he was presenting the morphology of solar system. And its first geometric proof was also provided in 1838 by Swiss geometer Jacob Steiner. He told that if you are having a convex set, like if you see at this example, if you are having a convex set, what is the convex set? Geometrically, you can very well describe the convex set. Suppose you are taking any suppose there exists some points or 2 points in the set. These are the 2 points of the set. These are on the boundary. Naturally, these are on the boundary. And if you join these 2 points and the line does not lie inside the plane, then this is called convex set, right? So here I am considering this point and this point, both are from the domain, and if you join the 2 points, this red line is lying outside this space, and therefore this is the convex set. So Steiner said that if you are having such type of some convex set, then by flipping this area, this is the part. So this boundary is concave. If you flip this boundary, you get such type of curve. Now, if you look at the perimeter of this green one and the perimeter of this one, by taking this dotted portion with it, then this perimeter is same, this one and this green one. Both the perimeters are same. but it is very well observed that area, this area is greater than the green one. Similarly, if you take this point and this point, suppose you take this point and this point, this is after flipping, then if you join these 2 points, these will again represent the convex set. Again you flip this area, this portion, flipping you will get like this, and the perimeter of this portion, is the same as the perimeter of the portion before flipping. So perimeter is same, but again it is apparent that this new area is bigger. This is bigger than the previous one. Likewise, you can flip this one. So in this way, finally you will get a shape which is of circle, a circular shape, and naturally this circular shape will have the greatest area. In second figure also you can see that if you squeeze this ellipse from the 2 sides and you expand this from these 2 sides, finally you will get a circle, and this circle will have the area which is greater than the area of this ellipse. While the perimeter is same, this is the perimeter and this is the same, both the perimeters are same. So in this way we see that the geometrical proof is also possible. Eiler in 1744 gave a mathematical method for it with the help of multiplier. But what happened, he provided the method where he got the Eiler Lagrange equation, which I told you in my previous lecture. The problem was that if I say for the problem without condition, then there was then the problem was that if the problem was to extremize a functional say I, j or anything, extremize a functional, I am writing it as I, y, iy, extremize a functional iy is equal to, say it is from x1 to x2 and defined as with the integrand y dot x dx. I have to extremize this functional such that y at x1, say it is having some value a1 and y at x2 is having some value a2. To extremize this functional, here the I is defined on a set, so it is a defined on a set of functions. Here y is equal to fx, f is defined from r cube to r and y is defined from x1, you can say that it is going from even x1 to x2 to r, right? Now To extremize this functional, Eiler provided a condition which was known as Eiler-Lagrange's equation. He provided that if a curve satisfying the equation delta f delta y minus d dx of delta f delta y dot is equal to 0. A curve satisfying this equation will provide the extremum of 1. Right? Now, in isoperimetric problem, we have another condition. You have one functional, this type, you have one functional to extremize, and you have some another functional which is a constant, which is working as a constant. So now our problem converts in terms of theory. It converts to a problem in which you have to extremize a function subjected to certain condition. So now what is the problem? Now the problem is to extremize a function which is actually a functional, extremize a function, say it is fy, subject to problem is to find a curve, find a function or curve which extremize a function, this one, subjected to the condition say gy, g is another functional, f is one functional and g is another functional, x1 to x2, say it is g, y, y dot, x and dx. So if you again look at your isoperimetric problem, it is saying find a closed curve. This is a find a function. What is this function? This function is a curve. So find a closed curve such that it encloses maximum area. So what is your extremum function here? It is the area function, such that perimeter is fixed. Yeah, given. So what is the condition? This is the condition. And here what is the condition? This is the condition. When you are talking about perimeter, perimeter is a function defined on curves. So again it is a functional. Area is a functional. So you have two functionals. This functional is providing one integral, this functional is providing another integral, but this is fixed. So your problem converts to finding a curve or finding a function which is extremizing this one subjected to this condition. Here are certain other conditions on y. Eiler, they provided its solution in terms of multiplier. He introduced a multiplier method to solve this problem in 1744. But then after 10 years, Lagrange found another solution, and he wrote a letter to Eiler and sent his solution to send him his solution, his new solution. And in that solution he suggested some new notations of variables, and Eiler was so impressed with the solution of Lagrange that he dropped his name from the method. He gave the credit to the Lagrange, and finally the method was known as Lagrange multiplier method. Now, what is the Lagrange multiplier method? From theory point of view, we will derive the method. This is Lagrange multiplier method. We use this method in simple calculus, where we have some function, we have to extremize it, and the function is subjected to certain constant. Here again you are having a function, but this function is in terms of integral, and naturally it is subjected to a condition which is again in terms of integral. So we will use calculus of variation technique. So what we do in the Lagrange multiplier method, we know that our problem is to extremize 1 subjected to 2. Suppose I say that 1 is denoted by I. Let I is equal to Fy is to be stationary, subjected to say G is equal to Gy. हम इसको J ले लेते हैं, थोड़ा फर्क हो जाएगा. Subjected to J is equal to Gy. So to find the correct path, the closed curve, the correct path say y is equal to yx, we will consider the neighboring path. Consider the neighboring paths designated by the parameters say alpha 1 and alpha 2. Now this is the method, because here you have two integrals. So in this method we consider the two parameters. How we write the neighboring paths? To write, suppose you are having this one curve y is equal to fx, then with the help of these two parameters you will get some neighboring path. So to write this neighboring path, we define two auxiliary functions. Define auxiliary function eta 1 x and eta 2 x, such that eta 1 is defined from x1 to x2 to r, and eta 2 is defined from x1 x2 to r. Eta 1, eta 2 and y, these are certain condition, are well behaved functions These are continuous and non-singular in x1, x2 and are having first and second order derivatives. In this interval. So these are certain conditions on eta 1 and eta 2. Now I will define the neighboring paths. Define y x alpha 1 alpha 2, because now you are taking two new parameters alpha 1 and alpha 2. It will be y x 0 0 plus alpha 1 eta 1 x plus alpha 2 eta 2 x. In this way we have defined a neighboring path where eta 1 and eta 2 are 0 at the endpoints of each path. What does it mean? Suppose this is your one path, this is your another path, this is your another path. So at the end point there is no variation, and eta is representing the variation. So this variation is 0 at the end points. Right? Now in terms of these new parameters, if I define I, 1 and 2 will be written as I in terms of y alpha 1 and alpha 2, or I will write it as only alpha 1 alpha 2. Then it is x1 to x2. There was function of y, and this y is a function of x alpha 1 alpha 2. It is a function of y dot. Again y dot is a function of x alpha 1 alpha 2, and it is a function of x also. It is dx. And j is again a function of alpha 1 alpha 2. It is x1 to x2 g of y function of x alpha 1 alpha 2 x alpha 1 alpha 2 and x. So we will define I and j in terms of the new parameters. Now we choose a multiplier. Let lambda be the Lagrange's multiplier. Then define what we'll do. We'll multiply this one by lambda, which is the given condition. So define k, which is I plus lambda j. So we define a new functional k with the help of I and j. Then your k will be x1 to x2 f plus lambda g dx. You write this f plus lambda g, let f plus lambda g is equal to h. Right? Now you have to extremize this I. To extremize I, the process is that we take the partial derivatives of k. Naturally, k is a function of alpha 1 and alpha 2. So, delta k is 0 for variations with respect to alpha 1 and alpha 2. And how can we write it? We can write it as delta k delta alpha 1 is 0 and delta k delta alpha 2 is 0. So 6 implies delta k delta alpha 1 is delta delta alpha 1 h, and this h is naturally f plus lambda g, and h is a function of y dot x dx from x1 to x2. This should be 0. I'll open it because these are free from alpha 1, these are independent of alpha 1. So I'll enter this, I'll exchange these two, partial derivative and integral. So delta k delta alpha 1 is equal to x1 to x2 delta delta alpha 1 h. H is a function of y dot and x, right? x1 to x2 इसको डिफ्रेंशिएट करेंगे अल्फा 1 के रिस्पेक्ट में, डेल्टा एच डेल्टा अल्फा 1 सॉरी डेल्टा एच डेल्टा वाई डेल्टा अल्फा 1, देन डेल्टा एच डेल्टा वाई डॉट डेल्टा अल्फा 1. And if I write delta h delta x delta alpha 1, then this will be 0 because there is no variation in x with respect to alpha 1. So it is 0. This is dx. And this should be 0 for maxima and minima. x1 x2 delta h delta y delta alpha 1 dx plus delta h delta y dot, I may write it as dtx of delta y delta alpha 1. Again solve it. Integrated as the product of two functions, delta h delta y dot ऐसे ही रहेगा, इसका इंटीग्रल डेल्टा y डेल्टा अल्फा 1 for the limits x1 to x2 minus derivative of delta h delta y dot and integral of this second term यानी delta y delta alpha 1 dx. Now what is its value at x1 and x2? This is 0 because there is no variation in y with respect to alpha 1 at the end points. Again, what is delta y delta alpha 1? This is eta 1 and eta 1 is 0 at x1 and x2. So this will vanish. Combine these two. This is 0, this is 0. x1 to x2 delta h delta y minus ddx of delta h delta y dot delta y delta alpha dx is 0, delta alpha 1. Now this is eta 1 x and eta 1 is a smooth function. Now by fundamental lemma of calculus of variation, because your y and eta x are satisfying its conditions, this integrand will be 0. So this implies delta h delta y minus d dx of delta h delta y dot is equal to 0. Now put the value of h delta delta y. The value of h we have taken as, this is h, f plus lambda g. So we will put this value f plus lambda g minus d dx of delta delta y dash f plus lambda g is 0. Write it as two parts, one with lambda and one free from lambda. Delta f delta y minus d dx of delta f delta y dot plus lambda delta g delta y minus d dx of delta g delta y dot is 0. Similarly, if you find delta k delta alpha 2 is 0, if you look at this equation is free from alpha. Similarly, if you find delta k delta alpha 2 is equal to 0, derivative of k with respect to alpha 2 0, you will get the same equation. So this is the condition. This is Eiler Lagrange equation, and the curve which will satisfy this equation will provide the extremum solution. So what is the difference between the problem of extremal, in which we had only one integral, there was no condition, there we get only this portion, and if it is subjected to certain condition which is represented in terms of g function, then you are getting this additional expression, this additional expression is here. So it is Lagrange's equation, Euler-Lagrange equation, which we will use for isoperimetric problem. So now we come to the solution of isoperimetric problem. Now solution of isoperimetric problem. The problem is to find a closed curve, find a closed curve such that it encloses a maximum area for a given perimeter. So whatever you have to extremize is area and condition is on perimeter. So we have, the problem is mathematically, the problem is to extremize, not to extremize, to find a curve which will extremize. Problem is to find a curve such that I is equal to, what will be the maximum area? For that, if I take some curve, let it be AB, and I have a portion of it such that this is ds, I take it dx, and this is dy. Then naturally area is take it as xy. So this is y, this is area. Area is I is equal to, for this elementary strip, it is y dx. So the problem is to find a curve such that I is extremum if some range for x is given, we will put it here, otherwise we will write x1 to x2 or whatever points are you taking on the two ends, such that given perimeter. Now what is the perimeter? Such that j is equal to x1 to x2 ds is given. What is ds? Small portion of it is ds, and if you take the whole from a to b, it will be x1 to x2 ds. और मान लेते हैं इसको कुछ x1 to x2 dx square plus dy square is equal to, say it be L. It is given x1 to x2 1 plus dy dx square dx is L, or 1 plus y dot square dx. So if you look at 1 and look at 2, then 1 implies, what is your f? f is y. यहाँ पर जो f आया फंक्शन इंटीग्रैंड जो आया वो y है, and 2 implies what is g? g is equal to root 1 plus y dot square, right? So this implies what is h? h is f plus lambda g. So either you write in this way or you direct write the equation. It is y plus lambda root 1 plus y dot square. Now we'll write the equation. Now Eiler Lagrange equation for multiplier. You have taken the multiplier. Lambda is Lagrange multiplier. ठीक है, आयलर लेग्रांज इक्वेशन क्या बन गई? डेल्टा h डेल्टा x माइनस डी डी एक्स, it is y of delta h delta y dot is equal to 0. But you know that this f plus lambda g, this f plus lambda g is this one, and this is free from x. So you can write the Beltrami condition, or you can take this one. It is up to you. If I take this one as such, then what I get? डेल्टा एच डेल्टा वाई. सो एच को डिफ्रेंशिएट किया वाई की रिस्पेक्ट में, 1 प्लस ओनली 1, दिस विल बी ओनली 1 माइनस डी डी एक्स ऑफ डेल्टा एच डेल्टा वाई डॉट. सो इट विल बी lambda y dot upon root 1 plus y dot square, and this is equal to 0. Or you may write derivative of lambda y dot 1 plus y dot square is equal to 1. We will integrate it and get lambda y dot 1 plus y dot square is equal to it was 1, so 1 ka integral x, and take one constant of integration. I am taking this as minus a. You may take it plus a also. So to solve it, square the two sides. Lambda square y dot square is x minus a square 1 plus y dot square, which may be written as x minus a square plus x minus a square y dot square, or y dot square is x minus a square upon lambda square minus x minus a square. सॉल्व कर लिया इसको. y dot is x minus a square root of lambda square minus x minus a square. So what is y? Integrate the two sides. X minus a root lambda square minus x minus a square plus some another constant of integration. Now you solve it, and solving you may put this one as t, and it is a simple solution, and solving you will get an equation which will be of the form x minus a square plus y minus, there will be some constant, say it is c square is equal to lambda square. So what is this shape? This is the shape of a circle. तो आइसोपेरिमेट्री में ये आ गया कि शेप तो सर्किल की होगी. अब लैम्डा इज अननोन विच इज रिप्रेजेंटिंग अ सर्किल. अब इसका एक सेकेंड पार्ट ये होता है कि हमें ये लैम्डा पता करना होता है कि ये लैम्डा क्या है, राइट. हम यदि जो एक गिवन कंडीशन होती है उसकी हेल्प से कोशिश करते हैं कि लैम्डा के लिए कोई इक्वेशन हमें मिल जाए. तो हमारी जो गिवन कंडीशन थी वो कंडीशन थी, एक मिनट इसका नंबर देख लेते हैं क्या आ रहा है. 3 के बाद दिस इज 4. सिंस हमें ये दिया हुआ था इंटीग्रल रूट 1 प्लस वाई डॉट स्क्वायर डी एक्स इज इक्वल टू एल, ये दिया हुआ था. तो हम क्या करेंगे, किसी भी तरह से इसकी वैल्यू रखेंगे 1 प्लस वाई डॉट स्क्वायर की. तो ये हमारे पास एक है इक्वेशन, ये वाली इक्वेशन यहाँ से उठा लेते हैं हम. व्हाट इज़ वाई डॉट स्क्वायर, तो ये सॉल्व हो जाएगा. रूट 1 प्लस एक्स माइनस ए स्क्वायर अपॉन लेमडा स्क्वायर माइनस एक्स माइनस ए स्क्वायर डी एक्स इज इक्वल टू एल. फिर इसको थोड़ा सॉल्व कर लीजिए, तो ये आएगा लेमडा ऊपर रह जाएगा, एलसीएम लेने के बाद ये कट जाएगा, और ये आ जाएगा लेमडा बाहर आने के बाद लेमडा स्क्वायर माइनस एक्स माइनस ए का स्क्वायर इज इक्वल टू एल. ये साइन इनवर्स का फंक्शन आ रहा है. दिस विल बी सॉल्व्ड टू गेट lambda sin inverse x minus a upon lambda, and this is for the limits x1 to x2 is L. So you can say that the solution has been found. It is a circle which will extremize your function. It is a circle which is enclosing the greatest area and whose perimeter is fixed. So with the help of that perimeter you will say that this is the equation of a circle, and this lambda may be found with the help of fifth. So 4 is the curve, closed curve, where इसको और लिख दो, closed curve enclosing the largest area where lambda is given by 5. So this is your complete solution of the isoperimetric problem. Similarly, you can use this Lagrange's multiplier method in some another mechanical problems, like I am giving you two problems in the assignment. One is prove that the sphere is the solid surface of revolution which for given surface area has maximum volume. अब आपके दो जो इसमें फंक्शनल हैं वो क्या क्या है, एक तो है वॉल्यूम और एक है एरिया, दो फंक्शनल है इसमें। तो एक्सट्रीमाइज किसे करना है, वॉल्यूम को। आई क्या बना आपका, वॉल्यूम, और गिवन कंडीशन क्या है, सरफेस एरिया गिवन है, तो जे क्या हो गया, गिवन सरफेस एरिया। तो आई भी मिल गया, जे भी मिल गया। आपको आई और जे से एफ प्लस लेमडा जी निकालना है और फिर उसी तरह से लैग्रेंजेस मल्टीप्लायर मेथड से सॉल्व कर देना है। मतलब लैग्रेंज इक्वेशन लग जाएगी, आयलर लैग्रेंज इक्वेशन। दूसरे में है फाइंड द शेप एज्यूम्ड बाय ए यूनिफॉर्म रोप व्हेन सस्पेंडेड बाय इट्स एंड्स फ्रॉम 2 पॉइंट्स एट इक्वल हाइट्स। 2 पॉइंट है इसके, 2 पॉइंट इक्वल हाइट पर है और इस तरह से ये सस्पेंड हो गई है। जो आइसोपेरिमेट्रिक होती है ना, वहां पर तो क्लोज्ड कर्व होता है, यहाँ पे आपका कुछ भी हो सकता है, कैसा भी कर्व हो सकता है, लेकिन इसमें हम लैग्रेंजेस मल्टीप्लायर मेथड लगा रहे हैं। तो इस तरह से रोप है सस्पेंडेड, दो एंड से, दोनों एक ही लेवल में है, इक्वल हाइट पर है, फॉर विच पोटेंशियल एनर्जी इज मिनिमम। अब यहाँ पे आपका जो आई है वो क्या है, पोटेंशियल एनर्जी फंक्शनल है, तो आई तो यहाँ से निकलेगा जिसे आपको मिनिमाइज कराना है। और क्योंकि यूनिफॉर्म रोप है तो ये रोप की लेंथ को आप फिक्स मान लेंगे, तो पेरीमीटर फिक्स हो गई, वो जे बन गया। एक आई मिल गया, एक जे मिल गया। अब दोनों की हेल्प से आप इसको लैग्रेंजेस मल्टीप्लायर मेथड से निकाल सकते हैं। तो आप इसे सॉल्व करके देखिएगा। एंड दिस इज ऑल अबाउट दिस लेक्चर। थैंक यू।